All right, we have lesson 5.1. 5.1 is about monomials. Well, it's about polynomials and different properties of polynomials and how to use them. More specifically, at first we'll be talking about monomials. And remember, monomials, taken directly from your vocab packet, is an expression that is a number, a variable, or the product of a number and one or more variables. So again, that basically just means that there's one term in any monomial. So things that are monomials would be like x or y, or if we have negative 3x, again, since it's two different things just being multiplied, that is a monomial. Or if we had 5x z to the second power y, that is a monomial because all of them are just being multiplied together and not added. Things that monomials are not would be like x plus 2. It is not because it has the plus. Or if we have 3y minus z to the fourth, that again is not a monomial because it has that minus within there. So anytime that you have the plus or the minus giving more than one term, so two terms here, in these cases, the two-term ones are called binomials. Binomial is a polynomial that has two terms. You can think of a bicycle for binomial. Bicycle is an instrument that has two wheels, two cycles, bicycle. So a binomial is a polynomial that has two different terms. Or for the monomial, you can think of Mr. Peanut. He has a monocle, which is a device with one singular lens that is used to correct vision for one eye. Monocle, monomial. The mono just implies that there is one. So we'll be using monomials for this lesson. So first off, we're going to be simplifying expressions of monomials with multiplication. Now, going longhand version on this one, we notice that we have, again, just two monomials. These ones are considered monomials because there is no addition or subtraction in them, even though they have that negative in front, the negative 2a to the third power b and negative 5a b to the fourth power. Those are just one term. That sign in the front means that it's negative, not that it's being subtracted from anything. So those still just have one term and thus are monomials. So if we want to, as I said, longhand multiply them, we can start with our constants. Our constants are the ones that are just the numbers with no variable. So we'd say that we have negative 2 times negative 5. Those are our constants being multiplied here. Then looking at our first variable, a, from the first monomial we have 3 a's, so times a times a times a. And from our second monomial we just have 1a. There's kind of an implied 1 power there. So times 1 of the a's. Then from our first monomial we have 1b. And from our second we have 4 other b's. So 1, 2, 3, 4. Now in the end, we have kind of this large multiplication expression here. Now, even though they have the negative signs in front, that doesn't mean anything's being subtracted. They are all still one term here. So if we combine our constant terms, negative 2 times negative 5 is a positive 10. If we combine all of our a's, all of our a variables, we notice that there are 4, so it is a to the fourth. And if we combine all of our b's, we notice that there are 5 of them, so b to the fifth. In the end, our answer is 10, a to the fourth, b to the fifth. Now, if we wanted to see that same process happen, but not in the longhand way, we can kind of jump the gun, and instead of writing every single thing out, we can just do things in different steps. So we'll start by noticing again our constants first. Negative 2 times negative 5 is just 10, positive 10. Now we have a to the third power here, and again a to kind of that hidden 1 power that it's up to. Now 3 plus 1 is 4, so we know that when we're using exponent multiplication, you just add the exponents. So we have a to the fourth power. Similarly, we have a b to the 1 here and a b to the 4 over here. 1 plus 4 is 5, so we have b to the 5th power. So again, just like before, our answer becomes 10 a to the 4th, b to the 5th. So it doesn't matter which method you use to solve that problem, you will end with the same correct answers. Just please be sure that the math you are doing is correct. Moving on here, we have simplifying expressions with division. Now, a big thing to recognize on this one is that we are assuming s is not 0. If s was 0, we have s squared over s to the 10th power. That would mean that 0 squared equals 0 to the 10th power, which would be 0 squared is 0, and 0 to the 10th power is still 0. Even though it's 0 on top here, we have a 0 on bottom, and nothing, even 0, nothing can be divided by 0. You cannot do that. So we need to make sure that we are not dividing by 0 ever. But since we are assuming that s is not 0, we can continue with this one. So our s squared over s to the 10. Again, going longhand, we could write this out as s times s on the top, because that's s squared, or s to the 2nd power, over, we're going to have s to the 10, so there's going to be 10 s's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 s's in total. Now, once we have that there are 10 s's being multiplied on the bottom and our 2 on the top, we can recognize that an s on the top will divide out an s on the bottom. Again, an s on the top will divide another out of the bottom. Now on top, again, like before, we kind of have a hidden 1 here, 1 being multiplied by this. So in the end, we'll count up that we have 8 s's left on bottom, and the 1 is still what's left on top. So our answer becomes 1 over s to the 8. So this would be our answer in this situation, or this problem. Now again, if we didn't want to use longhand, there are other ways to do it. If we have s to the 2nd power and s to the 10th power, we can recognize that both of these have the same base of s. And anytime you have the same base, your exponents can subtract out. So if we subtract 2 from the top, that would leave us with 0, and 2 from the bottom, that would leave us with 8. Now, s to the 0th power is going to be 1. Anything to the 0th power is 1. And s to the 8th power remains as s to the 8th power. So again, we get the answer of 1 over s to the 8th.